Consider the mystery and complexity of our planet's history. Earth has existed for billions of years, and during this time, it has undergone unimaginable changes. Volcanoes have erupted, oceans have filled and emptied continents, glaciers have covered vast territories, and then retreated again. Have you ever imagined what Earth looked like before humans existed? It was teeming with life, but completely different. Giant trees that no longer exist, and strange creatures of which we can only guess based on fossilized remains. Human civilization, with its cultures, languages, and technologies, has only appeared on this stage for a brief moment compared to the grand history of the planet. We, who live now, are merely a fleeting moment in the vast expanse of time. Over billions of years, Earth has witnessed numerous evolutionary changes that have shaped its appearance. For instance, massive ice sheets that once covered the northern regions have left behind deep valleys and hills that we can observe today. These geological changes occurred long before humans appeared and continue to influence our lives, even though we often fail to notice them. From vast continents to tiny mineral details, all of this testifies to the fact that our planet has gone through many stages, many of which remain a mystery to us. In this boundless history, filled with secrets and discoveries, humans are just beginning to understand their place. We cannot ignore the fact that, in the scale of time, human civilization is but a tiny spark that ignited against the vast cosmic backdrop that surrounds us. Each of our actions, each discovery, is but a small part of this grand picture that continues, and Earth continues to change, even though we often fail to notice it. Within the planet's depths lie millions of years of history waiting to be revealed, and science, with each new discovery, brings us closer to understanding this complex and multifaceted history. Research shows that even today, millions of years after our planet's formation, changes are occurring beneath its surface that could reshape the landscape just as they did millions of years ago, confirming that Earth is a living entity that continues to amaze us. The age of Earth is approximately 4.5 billion years. This immense period of time is difficult to comprehend. For millions of years, the young planet slowly cooled, and the first oceans formed on its surface. Water collected in deep depressions, creating conditions for life, while volcanic gases gradually formed a protective layer around the planet. Over billions of years, the planet underwent changes. Continents shifted, mountains rose and collapsed, oceans changed their boundaries. During this time, the first single-celled organisms appeared on Earth, which became the foundation for complex ecosystems. Each change, each event in this long process, created prerequisites for the appearance of more complex forms of life. And in this almost endless time span, intelligence began to develop, slowly but surely, building civilizations and leaving its traces in the sands of time. This process, like the flow of a river, never stops, continuing to develop and change. As a result of all this, today we can study fossil remains that tell the story of Earth, from its formation to the appearance of the first humans. It is precisely due to this unique historical context that we can understand how not only ecosystems, but also culture, science, and technology have evolved. Scientific research shows that over these billions of years, life on the planet has passed through 5 mass extinctions, each of which altered the ecological landscape and opened new possibilities for evolution. The concept of deep time helps us understand the scale of Earth's history. If we imagine the geological timescale as a 24-hour day, then each hour would correspond to approximately 185 million years. In this context, the first simplest forms of life appeared around 4 billion years ago, which would be roughly 3 hours into the night. However, when it comes to Homo sapiens, they only appeared around 200,000 years ago, which is just the last 2 seconds before midnight. This means that all of human achievement, including the invention of writing, agriculture, and technology, occurred in these final moments. This perspective allows us to realize how insignificant our own experience and history are compared to the age of Earth. For instance, if we could observe this timescale, all wars, discoveries, and cultural achievements would appear as brief flashes in the endless sequence of geological changes. Human evolution, from its emergence to the present day, occupies only a tiny fraction of this vast temporal continuum, raising questions about the significance of our existence in the context of the planet and the universe. Scientific research in this field, such as the work done by geologists and paleontologists, helps us visualize this time, demonstrating how humanity is just one of many stages in the long journey of Earth's development. The Fermi paradox is a philosophical question that challenges why we do not observe clear signs of other intelligent beings in the universe, despite the vast number of stars and potentially habitable planets. This remarkable contradiction arises from the feeling that, given the infinite number of galaxies and planets, life should be ubiquitous. However, the facts speak otherwise. We have not found any compelling evidence of extraterrestrial civilizations. The statistics are striking. In our galaxy, the Milky Way, astronomers estimate there are between 100 and 400 billion stars, and about 20% of them could have planets suitable for life. Nevertheless, even with all efforts to search for signals from space or study exoplanets, the results remain modest. One aspect of the paradox is that, if intelligent civilizations do exist, they could have developed technologies capable of interstellar travel or long-distance communication. Yet none of these messages have reached us, raising numerous questions. Perhaps civilizations self-destruct before reaching such a level of development, or they choose not to contact other forms of life, or intelligent life is extremely rare. Meanwhile, each new astronomical observational project, whether powerful telescopes or missions to study other planets, only deepens the mystery and sparks new debates, underscoring that we are still on the path to understanding our place in the vast expanse of the cosmos. This concept is based on the analysis of geological and paleontological data, which indicate that Earth has experienced several mass extinctions, each of which significantly altered ecosystems. Schmidt and Frank explore the possibility that, for instance, during the Silurian period, which lasted from 441 to 410 million years ago, intelligent beings capable of creating technologies may have existed on the planet. Within this hypothesis, scientists consider various scenarios for life's development, including the possibility of complex ecosystems that could have supported intelligent life forms. They also discuss how such civilizations might have interacted with their environment, leaving behind artifacts that could be misinterpreted or even go unnoticed. A key aspect is the analysis of how we define civilization and the criteria we use to evaluate it. Scientists also emphasize that studying this hypothesis not only enriches our understanding of the past, but may also influence our perception of the future, particularly in light of contemporary climate and ecosystem changes. Thus, the Silurian hypothesis opens up new avenues for research and discussion, posing questions to which science currently has no definitive answers. As a result, valuable information about cultural and historical aspects of human life that once inhabited these territories is often lost. Meanwhile, their influence can lead to the formation of natural barriers, such as rivers and lakes, which can isolate certain regions, creating unique conditions for the development of new ecosystems and cultures. Therefore, the interaction between geological processes and human history creates a complex dynamic that necessitates a deep analysis and reinterpretation of many historical data. Archaeologists and geologists must collaborate closely to reconstruct the past, taking into account the influence of various factors that have been at play over centuries. Erosion is a powerful geological process that can wear down even the most solid and monumental structures to their foundations over millions of years. It occurs under the influence of various factors such as water, wind, and temperature changes. Additionally, acids in rainwater can corrode metallic and stone structures, turning metal into oxides and stone into sand. For example, in the ancient city of Petra in Jordan, built from pink sandstone, erosion has already caused significant damage to the unique facades that were once among the wonders of the world. Scientific research shows that each drop of rain and gust of wind can affect the preservation of historical monuments, making the study of erosion an important aspect of preserving cultural heritage. Tectonic movements of the Earth's crust represent powerful forces that shape the surface of our planet. Continental plates, composed of hard crust, are constantly in motion, colliding, diverging, and subducting beneath one another. Plates can also diverge, creating new oceanic floors, as in the case of the Mid-Atlantic Ridge, where plates move in different directions, allowing magma to rise and form new crust. When one plate subducts beneath another, it can carry away any archaeological finds, monuments, and even entire cities into the mantle. For example, these tectonic processes have been acting for millions of years, continually reshaping the world map and erasing traces of human activity. As a result, ultimately, many ancient monuments, such as Mayan temples or ruins of Roman cities, are at risk of disappearing due to these natural processes. The process of sediment accumulation occurs when various materials, such as sand, clay, and silt, settle to the bottom of bodies of water or onto the surface of the earth. These layers of rock form as a result of erosion, when wind and water break down rock formations and transport particles to new locations. Gradually, over millions of years, these sediments accumulate, forming multi-layered deposits that gradually bury everything created by intelligent beings. Over time, the lower layers are subjected to the pressure of the upper layers, leading to their compression into monolithic rocks such as limestone or sandstone. This process can take millions of years, and in the end, we obtain geological formations that carry the history of the Earth and its inhabitants. For example, compressed layers of rock serve as a kind of time capsule, preserving traces of the past that we can investigate today. It is important to note that these accumulations not only store information about life on Earth, but also shape the landscape, influencing its appearance and structure. Civilizations develop within what are known as time windows, which are specific periods when conditions for growth and prosperity are most favorable. These windows can depend on a multitude of factors, including climate changes, the availability of natural resources, social structures, and technological advancements. For instance, during periods when the climate was stable and predictable, societies could focus on agriculture and construction, leading to the formation of cities and cultural centers. In such times, people often united into complex social systems, created laws, and developed science and art. Conversely, when the climate became unstable and resources depleted, civilizations faced crises that could lead to their decline or even disappearance. This process can be observed in various cultures around the world, each of which has passed through its own time windows, transforming the appearance and structure of society. This determines which human achievements will endure through the ages and which will be forgotten. It is important to note that time windows are not static. They can open and close, creating new opportunities and challenges. Throughout history, some societies have utilized their time windows to create magnificent architectural structures, such as the pyramids in Egypt or the temples in Mesopotamia, while others, failing to adapt to changing conditions, found themselves on the brink of extinction. Thus, the analysis of time windows provides a deeper understanding of why some civilizations flourished while others declined. This approach allows researchers to examine not only causal relationships, but also the interconnection between human activity and the surrounding environment, tracing how changes in climate or resources could influence cultural and social changes. Ultimately, time windows offer a window into the past, enabling us to understand how our predecessors responded to the challenges of their time. In such conditions, researchers can identify patterns that help explain how, over the course of millennia, adaptation and innovation have shaped human societies. The Silurian period, which spanned from 443 to 419 million years ago, was a crucial stage in Earth's history when the climate underwent significant changes, creating conditions favorable for the potential development of intelligent life. During this time, the oxygen level in the atmosphere reached approximately 21%, which facilitated the active development of complex ecosystems. Temperatures were warm, averaging between 20 and 25 degrees Celsius, providing ideal conditions for life both in water and on land. Shallow seas teemed with diverse organisms such as trilobites and corals, which played a key role in the ecosystems of that era. Vegetation also began to develop rapidly. On land, the first terrestrial plants appeared, contributing to the formation of new ecosystems and increasing biomass. The Silurian period is also known for its geological processes, such as the formation of mountain ranges, which introduced various minerals and nutrients into the oceans, fostering the development of new life forms. Research indicates that there was a significant increase in biological diversity during this period, which could have paved the way for the emergence of more complex life forms. The conditions in the oceans were conducive to the development of ecosystems where a wide variety of species could interact and evolve. On land, the first vascular plants began to establish themselves in the soil, which could eventually lead to the creation of complex terrestrial ecosystems. It is worth noting that the presence of extensive coastal lines also contributed to the development of life forms that adapted to various conditions. Coral reefs formed underwater, providing habitats for numerous marine creatures and increasing the chances of new species evolving. The Silurian period marked a time when life on Earth began to take on more complex forms, preparing for future evolutionary changes that would lead to the emergence of more advanced life. Fossil records show that by the end of the Silurian period, complex ecosystems already existed, opening up new avenues for discussion about the possibility of the emergence of intelligent life. The Carboniferous period, which lasted from 359 to 299 million years ago, was an era when the Earth's atmosphere was rich in oxygen, fostering the rapid development of life. During this time, vast tropical forests dominated the planet, consisting of giant ferns and conifers that reached heights of up to 40 meters. The high oxygen levels, exceeding 20%, created ideal conditions for the existence of large insects, such as dragonflies with wingspans of up to 80 centimeters. These forests not only provided food for various herbivores, but also served as shelter for predators, contributing to the emergence of the first reptiles. While terrestrial ecosystems were developing on land, the seas were home to sharks and other predatory fish that dominated the aquatic environment. Additionally, during this period, coal seams were actively forming, resulting from the decomposition of vegetation, which later became a crucial resource for the industrial age. These coal deposits, formed from the remains of ancient forests, eventually became the primary source of energy for many civilizations. The Carboniferous period also saw the active development of amphibians, which began to colonize land, marking an important step in the evolution of more complex life forms. Scientific research of this period continues to reveal new facts about how our ancestors adapted to changing environmental conditions, helping us better understand the evolution of life on Earth. Notably, the Carboniferous period laid the foundation for the formation of ecosystems that would persist for millions of years, including the conditions that preceded the emergence of mammals and, ultimately, humans. The Permian period, which lasted from 299 to 252 million years ago, was a time of true flourishing for terrestrial ecosystems. During this time, Earth was home to diverse plants, including giant ferns and conifers that formed dense forests. These ecosystems provided ample food for a variety of animals, including early reptiles and amphibians. A distinctive feature of the Permian period was the appearance of the first mammals, which could serve as a foundation for the further development of more complex forms of life. Conditions were favorable for the formation of complex ecosystems that could support the development of highly organized societies. At this time, continents had extensive landmasses, which facilitated the migration of species and increased biodiversity. For example, on the territories of present-day China and Russia, there were vast plains where primitive civilizations could have developed. Some researchers even suggest that with a stable climate and sufficient resources, such civilizations could have reached a significant level of development. During this time, the climate on Earth was mainly warm, which promoted plant growth and animal diversity. However, all this splendor ended with a massive extinction event that occurred at the end of the Permian period and wiped out about 90% of all species on the planet. The mechanisms of extinction are still a subject of debate among scientists, but among the possible causes are volcanic activity and changes in the level of oxygen in the atmosphere. It is interesting to note that this mass extinction was the largest in Earth's history, bringing an end not only to many animal species, but also to the evolutionary path that could have led to the emergence of more complex forms of life. As a result, despite all the conditions for the development of civilization, it was this extinction that put an end to the possible flourishing of highly developed societies in that period. Soon after the extinction, nature began to recover, but it did so in a completely different context, where reptiles gave way to mammals. Throughout Earth's history, several great extinctions have occurred, which were catastrophic events that significantly altered the planet's biosphere. These global events led to a sharp decrease in biological diversity, erasing entire ecosystems and leaving behind empty spaces. Typically, such extinctions were caused by a combination of factors: climate change, volcanic activity, sea level changes, and even meteor impacts. They acted as powerful catalysts, forcing species to adapt or go extinct. Most often, life on Earth recovered, but in a new format. opening the door for new forms of life that previously had no chance of survival. From time to time, sudden changes in ecosystems provided opportunities for other species to fill the vacant niches. These great extinctions not only destroyed existing life forms, but also created conditions for future evolution, during which new species and ecosystems emerged. For instance, after one such extinction, mammals appeared on Earth and eventually became the dominant group of animals. As a result of evolutionary changes that occurred after the great extinctions, Earth's biosphere acquired new qualities that significantly differed from those of previous epochs. The Permian extinction occurred around 252 million years ago and was one of the most catastrophic events in Earth's history. As a result of this extinction, approximately 96% of marine species and around 70% of terrestrial species disappeared. The causes of this phenomenon continue to be debated among scientists. One of the most widely accepted theories links the extinction to massive volcanic eruptions in the region of present-day Ural, which released enormous amounts of carbon dioxide and sulfur into the atmosphere, leading to rapid climate change and acid rain. These changes disrupted ecosystems, destroying the familiar habitats of many species. Additionally, the hypothesis that this extinction was triggered by the impact of an asteroid or comet is also discussed, although the evidence supporting this theory is less convincing. The Permian extinction led to a complete reset of Earth's ecosystems, and life began to evolve in new directions. As a result of this event, new groups of organisms, including the first dinosaurs and mammals, emerged, marking the beginning of a new era in Earth's history. This extinction served as a turning point for further evolution, paving the way for the diversity of life forms that we observe today. A significant aspect of this process was the onset of the Mesozoic era, which was characterized by the dominance of reptiles and the formation of modern ecosystems. Archaeans and bacteria, which survived this extinction, became the foundation for new forms of life that adapted to the changed conditions. The Cretaceous-Paleogene extinction event occurred approximately 66 million years ago and was one of the most catastrophic events in Earth's history. Scientists believe that the primary cause of this mass extinction was the impact of an asteroid with a diameter of around 10 kilometers in the vicinity of the modern Yucatan Peninsula, which resulted in the formation of the Chicxulub crater. This event led to significant changes in climate and the environment. The release of dust and gas into the atmosphere blocked sunlight, causing a sharp drop in temperatures and halting photosynthesis. As a result, ecosystems that depended on sunlight were threatened, and many species, including dinosaurs, were unable to adapt to the new world. It is possible that if this extinction had not occurred, more advanced civilizations could have developed on Earth, coexisting with dinosaurs. Such civilizations could have been technologically advanced, given that complex ecosystems already existed on the planet. However, the asteroid's impact was not limited to the extinction of dinosaurs. It affected around 70% of all species on the planet. The loss of life in oceans and on land created gaps in ecosystems that were filled by other organisms, ranging from mammals to birds. The extinction of such large animals as dinosaurs freed up ecological niches, which facilitated the evolution of mammals that later became dominant on the planet. It is important to note that this mass extinction was not only a catastrophe, but also the beginning of a new era in which mammals had the opportunity to develop and adapt to conditions previously inaccessible to them. Scientific research shows that the asteroid impact served as a catalyst for significant changes in the biosphere, ultimately leading to the emergence of modern species. Archaeologists and paleontologists continue to study this period to understand how the changes occurred and which factors contributed to the survival of certain species despite global catastrophes. A significant fact is that events like the Cretaceous-Paleogene extinction highlight the fragility of life on Earth, where even the most dominant species can disappear in an instant. Geological markers are specific layers or features in rocks that can serve as evidence of various processes that occurred on Earth over millions of years. They preserve information about the chemical composition of the atmosphere, oceans, and even the biosphere at certain historical moments. These markers can indicate the presence of a technological civilization, as changes in the geological layer can be linked to human activity, such as mass production or resource extraction. For instance, changes in the concentration of certain elements or isotopes can indicate anthropogenic activity. which leaves traces in geological time. An important aspect is that such markers can be recorded not only in sedimentary rock layers, but also in other forms, such as minerals or fossils. These evidence can be utilized by scientists to analyze how human activity has impacted the planet, as well as to understand the possible future of our civilization. By studying geological markers, scientists can assess the level of technological development and its impact on ecological systems, which allows for a deeper understanding of how civilizations have formed and evolved throughout history. Unusual concentrations of rare metals, such as gold, platinum, and palladium in geological layers, have sparked interest among researchers as potential evidence of ancient mining and processing by intelligent beings. For instance, in the area of present-day Kazakhstan, high levels of copper and gold were found in layers estimated to be over 3,000 years old. This could indicate the existence of advanced mining techniques used before our era. Additionally, in some places on the Near East, abnormally high concentrations of lead and silver were found, suggesting that local civilizations were actively engaged in mining activities. Specifically, in the ancient ruins of Nineveh, archaeologists discovered traces of metal processing that point to the use of complex technologies such as smelting and casting. These findings suggest that some societies may have had organized systems of resource extraction and processing that were ahead of their time. In other regions, such as South America, the discovery of high concentrations of gold in geological deposits raises questions about how far ancient civilizations advanced in exploiting natural resources and what technologies they employed for this purpose. Notably, in places like the Pampas Plateau in Argentina, traces of ancient mines were found, indicating that mining could have been organized at the level of entire communities. As a result, such discoveries not only confirm the existence of metal processing technology, but also suggest that ancient civilizations may have had complex economic structures based on resources. The presence of rare metals in layers formed thousands of years ago raises questions about how technologies developed and how diverse they were in different regions. Anomalies in the isotopic composition of ancient rocks discovered by scientists raise intriguing questions about possible artificial nuclear reactions or other technological processes that may have occurred millions of years ago. For instance, in some samples of granites and metamorphic rocks, deviations in the ratio of carbon and oxygen isotopes have been observed, which may indicate abnormal temperature conditions or chemical reactions not typical of natural processes. In one discovery made in Australia, scientists found an increased concentration of uranium isotopes, which could suggest that processes similar to nuclear decay may have occurred in this region. Additionally, possess technologies that we do not yet understand. These prehistoric times, there are even speculations that such technologies could have been lost or forgotten, leaving only traces in the geological layer. For example, in India, stone artifacts were found that may be linked to anomalous isotopes in surrounding rocks, adding mysteries to human history and its interaction with nature. Such discoveries pose numerous questions for scientists about what these ancient technologies might have been, and in what specific context they could have existed, making the study of these anomalies particularly fascinating. Researchers also note that such isotopic anomalies may indicate more complex and diverse processes than previously thought. Research into ancient layers of ice and sedimentary rocks reveals that in some places there are possible traces of global pollution that could indicate industrial activity of a vanished civilization. For instance, in the ice sheets of Greenland and Antarctica, scientists have found abnormally high levels of lead and other heavy metals, which could have entered the atmosphere as a result of large-scale fuel burning or metallurgical activities. Similar findings have been registered in sedimentary rocks deposited on the ocean floor, where traces of hydrocarbons and toxic substances have been discovered, which also suggest the activity of ancient industrial processes. An example of this is the discovery in the Pacific region, where samples of deep-sea sediments contain traces of polychlorinated biphenyls, suggesting the possible use of chemical technologies known only to modern societies. In some cases, scientists have also noted the presence of carbon isotopes that are not characteristic of natural processes, which could indicate large-scale artificial production of carbon. These findings raise questions about the level of technological development of ancient civilizations and the potential damage they could have caused to the environment. It is important to note that such data helps to better understand the climate and ecosystem changes that occurred in the past, which in turn can provide insights into how we should approach contemporary environmental problems. Scientific research continues, and each new discovery brings us closer to understanding the complex interrelationships between civilization and nature. Archaeological methods are not applicable for detecting traces of civilizations that existed tens or hundreds of millions of years ago for several reasons. First, the age of these civilizations exceeds the time during which material evidence of their existence has been preserved. Fossilized remains, artifacts, and other traces that could confirm the existence of such ancient societies are subject to destruction by natural processes such as erosion, tectonic movements, and climate changes. Moreover, on such vast timescales, significant changes occur in geological layers, making it difficult to identify and interpret potential finds. Secondly, many cultural elements, such as language, customs, and social structures, do not leave a physical trace, further complicating the task. Even if we were to find something that might indicate the existence of an ancient civilization, it does not necessarily mean that we could adequately interpret its significance or context. The complexity of analyzing such ancient periods also lies in the fact that our knowledge of the evolution and development of human societies is limited, creating a vast gap in the data. In such a context, archaeology faces a challenge not only in searching, but also in understanding the possible cultural interactions and changes that could have occurred millions of years ago, when climate and ecosystems were entirely different. Considering all this, it is important to understand that even the most modern archaeological approaches have their limits when it comes to such ancient timeframes. Fossilization or petrifaction is an extremely rare phenomenon where only a minuscule fraction of a percent of organisms are preserved in fossil form. In practice, out of millions of species that have existed on Earth, only a few become fossils, and this is due to a multitude of factors. Humidity, temperature, and the chemical composition of the surrounding environment also play a critical role. Oxygen and microorganisms typically promote decomposition, while conditions favorable for fossilization are quite limited. For instance, soft tissues of animals and plants usually do not preserve, making their discovery as fossils impossible. Therefore, fossilized remains typically consist only of hard parts of organisms, such as bones or shells. This presents significant challenges for studying even relatively recent extinct species, let alone intelligent beings that may have existed millions of years ago. Additionally, during the fossilization process, further changes can occur, such as mineral recrystallization, which also hinders the identification of the original organisms. Consequently, the probability of finding fossilized remains of intelligent beings is extremely low, and archaeologists often encounter fragments that cannot provide a complete picture of how our ancestors looked and lived. The majority of fossil remains belong to marine organisms, which also narrows the possibilities for finding traces of terrestrial or highly evolved species. Fossilization does occur, but on the scale of the entire biosphere, it is more of an exception than the rule, making each discovery a true sensation. Metamorphism of rock formations is a process that occurs under the influence of high temperatures and pressure, leading to a complete change in their structure. In this process, initial minerals and textures transform, creating new rock types such as marble and gneiss. Temperatures ranging from 100 to 1000 degrees Celsius and pressures reaching several thousand atmospheres can completely destroy any previous characteristics of the material. For instance, limestone under metamorphism transforms into marble, losing all traces of its original structure, including any signs of processing or use by intelligent beings. During this process, the recrystallization of minerals makes it impossible to determine how and by whom these materials were used before their metamorphism. This transformation often takes place within the Earth's crust, where tectonic processes create ideal conditions for metamorphism. Additionally, metamorphic rocks are often found near subduction zones, where one tectonic plate descends beneath another, creating extreme conditions. In such places, one can observe how rocks that have undergone metamorphism can contain fragments of other rocks that have also been altered by high temperatures and pressure. For example, in the Alps or the Himalayas, one can see how metamorphism has not only changed the mineral composition, but also the geological history of the region, concealing any traces of ancient civilizations or their artifacts. Subduction is a process where oceanic crust descends beneath continental crust, leading to its melting in the Earth's mantle. This process occurs at the boundaries of tectonic plates, where one lithospheric plate moves downwards beneath another. For instance, in the subduction zone of the Pacific Plate beneath the North American Plate, the oceanic crust, composed of denser and heavier rocks, essentially disappears into the continental crust. The temperature and pressure in the mantle are high enough to melt this crust, carrying away any traces of civilizations that may have once existed on submerged continents. This means that beneath the oceans could lie ancient lands filled with artifacts and signs of life, forever lost due to the subduction process. For example, in the case of submerged continents like Zealandia, scientists believe that unique ecosystems and even human settlements could have existed there. However, as a result of subduction, we cannot obtain any evidence of this, as everything is consumed in the molten rocks. Thus, subduction results in irreversible losses for archaeology and history, as it not only alters the geological structure of the planet, but also destroys any possible traces of humanity left on these submerged lands. Alternative forms of intelligence explore the possibility of intelligence existing outside the framework of primates. This includes ideas that intelligence can manifest in various forms, different from the familiar human thinking and behavior. For instance, other organisms may employ unique methods of information processing and decision-making, which may be linked to their environment and evolutionary adaptations. Some of these forms of intelligence may be based on entirely different principles of perception than those used by humans, opening up avenues for studying aspects such as collective behavior, instincts, and reactions to external stimuli. This also leads to contemplation of how different species can develop their communication systems and social structures, which may be as complex as those of primates but appear completely different. For example, research into the behavior of certain organisms shows that they may possess the ability to plan and use tools, challenging traditional notions that intelligent reasoning is the exclusive domain of humans and their close relatives. This concept raises numerous questions about how we define intelligence and reason, and how broad or narrow our criteria should be for evaluating other forms of life. Research in this area can lead to new understandings not only of the organisms themselves, but also of how we perceive and describe intelligence in a broader context. From a scientific perspective, this opens up numerous avenues for further research, and each new discovery can challenge existing concepts of what it means to be a rational being. For instance, observations of the behavior of certain marine creatures question our understanding of how intelligence can adapt to completely different living conditions. The development of intelligence in reptiles, particularly dinosaurs, is a fascinating aspect of evolutionary biology. This group of creatures dominated the planet for over 150 million years and exhibited an astonishing diversity of forms and sizes. Among the most intriguing reptiles were the troodontids, which had relatively large brains compared to other dinosaurs. Their brains were quite developed, suggesting the presence of more complex behavior and possibly even early signs of intelligence. For instance, researchers hypothesized that troodontids might have exhibited social behavior, cared for their young, and even used tools, albeit indirectly. These dinosaurs differed from their kin not only in size, but also in the structure of their skulls, indicating the presence of more advanced sensory systems. It is important to note that throughout evolution, troodontids adapted to various environmental conditions, which could have contributed to the development of their cognitive abilities. Their hunting strategies and capacity for learning could have been key factors in their survival in competition with other species. The abundance of findings, such as fossilized eggs and nesting traces, confirms that these reptiles not only existed, but also had a complex social structure. They inhabited various ecosystems, from forests to open plains, which could also have influenced their behavior and development. Evidence suggests that troodontids may have hunted in groups, implying some level of social interaction and possibly primitive communication. Their anatomical features, such as serrated teeth, indicate the possibility of a diverse diet, including both meat and vegetation. This also raises questions about the flexibility of their diet and their ability to adapt to changes in the surrounding environment. Scientific research continues to delve deeper into the understanding of these remarkable creatures, and each new discovery challenges our previous notions about the development of intelligence among reptiles. Fossils found in North America and Asia confirm that troodontids were quite widespread, indicating their successful adaptation to various conditions. Cephalopods, particularly octopuses, represent an extraordinary example of potential intelligence development in the animal kingdom. They possess a complex nervous system with around 500 million neurons, comparable to the brain of a dog. This system enables octopuses to exhibit remarkable abilities in learning and memory. For instance, in laboratory conditions, octopuses successfully solve tasks that require not only intellectual effort, but also creative problem-solving. They can open jars to obtain tasty treats, indicating their ability to use tools. Studies show that octopuses can adapt to new situations and learn from experience, which is a sign of high cognitive development. In some cases, they can even remember human faces and distinguish them by appearance. Moreover, their ability to mimic and change color in response to their environment can be seen as a form of communication and expression of intelligence. Octopuses use their unique anatomy, including 8 arms, to explore their surroundings, allowing them to actively interact with it. These mollusks show interest in new objects, which also points to their curiosity. Considering all these facts, it becomes clear that cephalopods exhibit a high degree of brain development and consequently significant potential for intellectual growth. Research continues, and scientists continue to uncover new aspects of their behavior, which helps us better understand how intelligence has evolved in the animal world. Arthropods, particularly social insects, possess an extraordinary evolutionary potential that challenges traditional notions of intelligence and community. Ants, bees, and termites exhibit exceptional abilities in organizing and constructing complex architectural structures, such as anthills and beehives, which can reach several meters in height. These structures are not merely shelters, but true multifunctional ecosystems where each chamber performs specific tasks, from food storage to offspring rearing. For instance, termites build their nests from saliva and soil, creating ventilation systems that regulate temperature and humidity inside, allowing them to survive in the most extreme conditions. Social insects also have a unique communication system, using pheromones to transmit information about food sources and threats. This enables them to coordinate the actions of hundreds and thousands of individuals, which can resemble collective intelligence. Moreover, research shows that in some cases, the interaction of ants can lead to effects that cannot be explained by individual actions alone. For example, when encountering obstacles, they can change their routes based on the behavior of other ants, indicating a level of collective intelligence. Interestingly, some bee species can learn from each other, sharing information about the locations of flowering plants. This opens new horizons for understanding how complex communication and cooperation systems can be developed. Additionally, their societies have a clear division of labor, where each individual performs its role, which also resembles human societies. Although it is difficult for us to imagine what collective intelligence looks like in the world of insects, their abilities to work together and create complex structures challenge our understanding of what intelligence is and how it can manifest. In nature, scientific research in this area continues, and each new discovery adds details to the portrait of these remarkable creatures. Furthermore, understanding their evolutionary potential may provide keys to solving many mysteries related to the development of collective thinking in various forms of life. For example, scientists are beginning to recognize that successful survival strategies in nature may be linked not only to individual qualities, but also to how communities are organized. This process clearly demonstrates that it is not necessary to be closely related to adapt to certain conditions. For instance, in various ecosystems, creatures with similar physical characteristics can emerge, despite having entirely different evolutionary histories. Convergent evolution shows that the process of adaptation to the environment can lead to the same results in terms of form, function, or behavior, thereby highlighting the universality of natural laws. This means that, despite the absence of common ancestors, organisms can develop similar survival and adaptation strategies to their environment. Thus, the concept of convergent evolution opens up new horizons for understanding biological processes and demonstrates how the diversity of life can be shaped by similar ecological factors. Often, this leads to the emergence of similar adaptations, making the study of these processes particularly fascinating. For example, in conditions of limited resources, the same mechanisms can lead to similar morphological or behavioral adaptations, enabling different species to survive and thrive in competitive environments. Comparative analysis of such adaptations can provide scientists with insights into many mysteries of evolutionary biology. The eyes of these two groups of organisms perform similar functions and even have analogous structures, despite their ancestors evolving in different environments and conditions. In vertebrates, such as fish and mammals, eyes have a complex structure with a lens, cornea, and retina, allowing them to effectively focus light and perceive images. Meanwhile, the eyes of cephalopod mollusks, such as octopuses, also possess highly developed capabilities, including movable pupils and extraordinary visual acuity, but they have a completely different anatomical basis. Instead of a lens, they have a system based on cones and pyramidal cells. These eyes, despite their differences in structure and origin, perform similar functions, illustrating how adaptation to similar environmental conditions can lead to the emergence of similar biological solutions. It is important to note that the eyes of these groups have evolved independently of each other, making them an example of convergent evolution. Research shows that such mechanisms can lead to similar results even in the absence of a common ancestral line, highlighting the incredible diversity of paths that nature can take to find solutions for the survival of species. Remarkably, octopuses and some species of vertebrates, such as sharks, even have similar light perception mechanisms, enabling them to hunt in low-light conditions. Comparing these two visual systems opens new horizons for the study of evolutionary processes and demonstrates how complex these adaptations can be. Convergent evolution of echolocation in bats and cetaceans is a striking example of how different animal groups can develop complex sensory systems in response to similar ecological pressures. Bats, which were the first to master echolocation, use sound waves for navigation and hunting insects in darkness. They emit ultrasonic signals that reflect off objects, allowing them to determine distance, size, and even texture. Meanwhile, cetaceans like sperm whales and dolphins have developed a similar system adapted to the underwater environment. Their echolocation not only helps them orient themselves in water, but also find food at great depths where light does not penetrate. It is interesting to note that both groups use different sound frequencies, which is related to their habitat. Bats typically emit high-frequency sounds, while cetaceans operate in a lower frequency range, allowing them to transmit signals over long distances underwater. This underscores how ecological conditions influence the evolution of sensory systems. The diversity of echolocation forms also demonstrates how different animal groups, despite their evolutionary independence, can arrive at similar solutions to the same problem, ensuring survival in a competitive environment. For instance, research shows that some dolphin species have developed echolocation to the point where they can not only detect fish, but also smaller objects like plankton. Ultimately, echolocation in bats and cetaceans serves as a clear example of how the same ecological challenge can lead to the formation of similar but uniquely adapted biological systems. Convergent evolution of intelligence in primates and corvids demonstrates how high cognitive abilities can emerge in various evolutionary lineages, despite different ecological niches and biological ancestors. For instance, chimpanzees can use sticks to extract termites, indicating that they possess planning and an understanding of cause and effect relationships. On the other hand, corvids like crows and jays have also shown remarkable cognitive abilities. Research shows that crows can solve puzzles requiring multi-step actions and even create tools from available materials. These birds are capable of learning and remembering the location of food hidden in various places, which also indicates their high memory and spatial understanding. It is interesting that both of these classes of animals have achieved similar results in the evolution of intelligence independently of each other, highlighting the universality of these adaptations. Research shows that corvids and primates share similar neurobiological mechanisms, suggesting that the complexity of their behavior is not only related to the size of their brains, but also to their structural organization. For example, in the brains of corvids, areas responsible for information processing are found, similar to those present in primates. This indicates that high cognitive abilities could have developed in the most diverse groups of animals during different geological epochs. adapting to their unique living conditions. Consequently, we see that regardless of whether they live in trees or in the air, primates and corvids serve as bright examples of how intelligence can evolve in response to similar environmental challenges. Scientific research conducted in the last decades confirms that these species can solve tasks requiring abstract thinking and planning, making them some of the smartest animals on the planet. The concept of technological singularity refers to a moment when technological progress becomes so rapid and irreversible that humanity cannot predict how exactly its life will change. This phenomenon is based on the idea that accelerating technological development leads to the creation of conditions for the emergence of even more advanced technologies, resulting in a cascading effect. Civilization development begins to follow an exponential curve, where each new innovation significantly exceeds the previous one in complexity and impact. In such conditions, old models of understanding and forecasting become obsolete, and people are faced with the need to adapt to new realities that may be unfamiliar and even threatening. This also raises numerous philosophical and ethical questions about how to manage such progress and what consequences it may have for social structure and individual life. It is important to understand that singularity is not just a technical phenomenon. It affects all aspects of life, including the economy, education, and human interaction. Sudden changes in society can have both positive and negative consequences, forcing people to re-evaluate their values and approaches to life. In this context, an interesting paradox emerges. The faster technologies develop, the more people begin to realize the need for a critical approach to them, questioning how these technologies affect personal and collective rights, freedoms, and identity. Thus, singularity becomes not only a technological process, but also a significant stage in the evolution of human thought and interaction. It is important to note that such changes require society not only to accept new technologies, but also to understand their essence and potential future consequences. Initially, people used simple stones for hunting and food processing, but by the end of the Stone Age, more complex tools like knives and spears emerged, significantly increasing their chances of survival. Then, each new discovery, whether the invention of the wheel in the 3rd millennium BCE or the development of writing in Mesopotamia, accelerated the pace of progress. The modern scientific achievements, such as satellite launches and space flights, became possible due to these technological breakthroughs. Considering that humanity has traveled this path in just a few thousand years, one might ponder how technology could have developed among other intelligent species. Their evolutionary trajectories and social structures, similar to ours, could have led to similar or even more impressive technological achievements. Imagine a space fleet created by a civilization that evolved on another planet, possessing unique resources and conditions for progress. For example, if intelligent beings on a planet with high gravity could develop technologies to overcome these physical limitations, their achievements could be entirely different from ours. Thus, technology does not simply develop linearly. It grows exponentially, and the more complex societies become, the faster they adapt and develop their tools and means. In the last 100 years, humanity has made strides that once seemed fantastical, from the first space flights to the colonization of other celestial bodies. The concept of the technological horizon posits that once a civilization reaches a certain level of technological advancement, it becomes invisible to external observers. This can, for instance, when the level of technology reaches a point where resources begin to deplete and the ecosystem can no longer sustain the previous way of life, society may either adapt by finding new sources of energy and materials, or collapse under the pressure of its own inventions. Throughout human history, there are numerous examples of civilizations, such as the Maya or the Hopi, that reached their technological peak but then faced ecological catastrophes leading to their decline. It is intriguing that some scientists suggest that contemporary society is following a similar path, where a growing population and resource consumption could lead to social and ecological disasters. In essence, the technological horizon could be the line beyond which civilization either takes a step forward or disappears into oblivion, leaving behind only traces on the Earth. Modern technologies, such as artificial intelligence and biotechnology, already spark debate about how they might alter society and whether they will lead to an improvement in life or its ultimate destruction. For example, the use of algorithms and automation in production creates new jobs, but also eliminates old ones, creating social inequalities. Archaeological visibility is a concept that reflects how various materials and technologies leave traces in the ground, and how these traces can be interpreted by scientists. It depends on numerous factors, including the physical properties of materials, their durability, as well as burial conditions and the surrounding environment. For instance, some substances decompose over time, while others can persist for thousands of years, influencing how we reconstruct the past. Additionally, the technologies used in different cultures can create unique traces that we can uncover during excavations. Archaeologists analyze these traces to understand how people utilized available resources and which technologies were prevalent in a particular historical period. It is important to note that archaeological visibility is not universal. Some materials may be more visible in certain conditions and less so in others, setting certain limits for interpretation. Research shows that the choice of materials and methods of their processing can significantly impact our perception of historical events and social structures. Technological advancements often serve as the foundation for the formation of archaeological finds and their subsequent study. For example, the methods used by ancient people can leave various types of traces, allowing archaeologists to draw conclusions about cultural practices and interactions between communities. Stone, for instance, granite formed from magma can remain largely unchanged over long periods if it is not subjected to destructive forces such as erosion or chemical weathering. However, even ancient stone structures like the pyramids in Egypt or the temples of the Maya are not always able to survive the centuries. This is due to the impact of natural disasters, climate change, and human activity. Additionally, some types of stone are susceptible to weathering under the influence of oxygen and moisture, leading to their destruction. For example, in Mesopotamia, many temples and cities made of limestone and clay have disappeared due to changes in water levels and the effects of sandstorms. This highlights that the durability of stone is not absolute, and its ability to remain in its original form depends on numerous external conditions. As a result, many architectural landmarks that once stood proudly on the earth may be lost forever if they are not properly protected or if natural conditions change. Archaeologists often encounter sites where once there were magnificent structures, but now only stone fragments or even no trace of their existence remain. Metals, even the strongest alloys, are not eternal. Over geological timescales, they undergo corrosion and oxidation, leading to their destruction. For instance, iron, despite its strength, begins to rust within just a few decades if not protected from moisture and oxygen. Steel, alloyed metals, designed to increase resistance to corrosion, are not a panacea. Even stainless steel loses its protective properties over time, resulting in the formation of corrosion cracks. Consequently, under the influence of the surrounding environment, any metallic objects can be completely destroyed over several thousand years. For example, in the Roman aqueducts built more than 2,000 years ago, signs of corrosion can be found, despite their initial status as technological marvels. Even this leads to the fact that many artifacts once considered durable are now seen only as rusted fragments or corroded remnants. Practically all metallic structures, whether statues, tools, or architectural elements, eventually fall victim to corrosion. Statistics show that in some cases, corrosion can destroy up to 90% of a metal's mass over several tens of thousands of years. This makes metals less reliable than stone, which can preserve the traces of civilizations for millions of years. For example, wood, if not protected, can rot in just a few decades, especially in humid climates. Fabrics made from natural fibers are typically affected by microbes and insects, leading to their rapid destruction. It is known that paper made from wood pulp can last up to 100 years, but under the influence of light, moisture, and oxygen, this period is significantly reduced. Nevertheless, on most excavations, researchers encounter emptiness where once there were objects that could tell stories about people's lives. Textile items that could have told of fashion and culture of their time rarely survive to our days, and even the most famous ancient civilizations, such as Egypt, have left only fragments of textiles. Therefore, studying the everyday life of people from the past becomes a real puzzle for historians and archaeologists, who must rely on indirect evidence, such as tools and pottery, to reconstruct the lost culture. Research results show that approximately 80% of all organic materials that existed in the past have been destroyed. The technological signature of civilization is a crucial element that helps us understand how various societies adapted to their environment and utilized the resources available to them. This concept encompasses unique ways in which cultures interact with technologies, reflecting their level of development and approaches to solving the challenges they face. For example, how certain societies used natural resources and adapted to climatic conditions can tell us a lot about their living conditions and worldviews. This signature is formed as a result of the interaction of various factors, such as geography, climate, access to resources, and cultural traditions. Thus, by studying the technological signature, scientists can reconstruct not only technological achievements, but also the socio-cultural aspects of human life in the past. This helps for example, the transition from simple tools to complex mechanisms may indicate an increase in scientific knowledge and changes in the social economic structure. Each such step leaves a trace, which when studied can provide insight into the time and place where it was created. Archaeologists actively study these signatures, and their findings help restore the picture of life in various civilizations, which in turn opens new horizons for understanding human history. Comparing the technological signatures of different cultures can also reveal how they borrowed and adapted technologies from each other, indicating interaction and exchange of knowledge between different peoples. The technological signature becomes the key to uncovering the complex interconnections between cultures, and its study continues, allowing us to look at the development of human civilization in a new light. It is important to consider that these signatures can be both positive and negative, depending on how technologies affect the environment and society. For example, some achievements may lead to the destruction of ecosystems, while others contribute to their preservation. Thus, research in this area raises many questions about how technologies shape our society and what legacy they leave for future generations. Researchers continue to seek new methods of analyzing technological signatures, using modern techniques such as radiocarbon dating and molecular genetics, which allow for a deeper understanding of the history of technologies. In addition, it is important to consider the influence of cultural context on the formation of technologies, as different peoples may interpret and apply the same ideas in different ways. For instance, this isotope has a half-life of approximately 5,700 years, enabling scientists to determine the age of archaeological finds. It is also, for example, the discovery of uranium ore in certain soil layers may suggest that the area was used for uranium mining, implying a certain level of technological activity. Furthermore, radioactive isotopes can serve as indicators of changes in ecosystems and human migration, allowing researchers to explore not only technological but also social aspects of ancient civilizations. The discovery of radioactive isotope traces in soil layers or fossilized remains can provide insights into how humans interacted with their environment and utilized natural resources. For example, in some regions where remnants of ancient civilizations have been found, scientists have detected elevated levels of isotopes that could have resulted from uranium enrichment activities. Such findings not only help date archaeological sites, but also shed light on technological achievements and their impact on nature. These materials, such as plastic, rubber, and synthetic fibers, do not decompose as quickly as organic substances and can persist in the environment for millions of years. For example, polyethylene, one of the most common plastics, can remain in nature for up to 1,000 years, forming unique geological layers that will testify to human activity. In some cases, these layers are already forming as a result of the accumulation of plastic waste and products, becoming embedded in soil and sediment layers, creating a sort of archaeological horizons for the future. Scientists have already discovered that microplastics are entering coral reefs and marine organisms, leading to changes in ecosystems. These synthetic materials can serve as indicators for future geologists studying our era. This phenomenon has become so relevant that scientists are developing methods to identify and classify these layers, opening new horizons for the study of our planet's history. There are even theories that future civilizations discovering these synthetic artifacts may learn about our level of technological development and way of life by analyzing these durable materials. Archaeologists have already begun to study sites where plastic and other synthetic substances are found in soil layers to understand how they might influence future geological research. Large-scale changes in landscapes and ecosystems can serve as significant markers of ancient civilizations in the geological record. For instance, changes in river courses caused by human activity can reveal much about the lives of our ancestors. Ancient civilizations like Mesopotamia actively modified landscapes by creating irrigation systems, which led to the formation of new ecosystems. For example, in Sumer, archaeologists found traces of ancient canals that altered river flows and facilitated the development of agriculture. The traces of these changes can be found in geological layers, where different types of soil and vegetation can indicate human interference with nature. Changes in soil composition due to agriculture can also be detected in geological records. For example, thus, it is important to note that these changes were not always positive. They could lead to the depletion of natural resources and ecological crises. For example, in some regions where intensive agriculture was practiced, there was a deterioration in soil quality, which could ultimately lead to the decline of civilizations. The analysis of these changes helps not only to better understand the past, but also to predict how similar actions might affect the modern ecosystem. The geological record can provide evidence of such changes, such as alterations in soil stratification and structure, which can indicate the presence of ancient cultures. Archaeologists and geologists continue to study these layers to reconstruct the picture of the lives of ancient people and their interactions with their surroundings. Scientific skepticism is an approach that helps critically evaluate unusual hypotheses and claims. This approach requires researchers not only to accept facts, but also to conduct a deep analysis of the evidence supporting these facts. In archaeology, this is particularly important when dealing with finds that may seem shocking or unconventional. For instance, the discovery of artifacts that might indicate the existence of highly advanced civilizations in periods when such civilizations should not have existed requires close scrutiny. Scientific skepticism helps separate truth from fiction, which is especially relevant in conditions where each new discovery can challenge historical understanding. This process not only strengthens scientific knowledge, but also contributes to a deeper understanding of human history and culture. In this context, it is important to remember that every hypothesis should be rigorously tested before being considered valid. Archaeologists can question conclusions based on insufficiently supported assumptions, allowing them to focus on facts and data that truly matter. Each new discovery requires careful analysis and verification, which is the foundation of the scientific method. As a result, even the most sensational finds are subjected to critical discussion, ultimately advancing our understanding of human history and culture. This practice of critical evaluation stimulates debates and generates new research that can lead to further discoveries and insights. Thus, scientific skepticism becomes an integral part of studying past civilizations, considering that each find contributes to the overall picture. Archaeologists identify various cultural layers by studying their age and context, providing a more comprehensive understanding of human history and the interactions between civilizations. The prince chosen. This approach not only simplifies scientific debates, but also helps avoid overly complex and confusing explanations that can hinder research. Scientists often use Occam's razor to evaluate the credibility of various interpretations of findings, which helps form clearer and more substantiated conclusions. This method has become the foundation for many modern scientific investigations, underscoring its importance in data analysis and theory formation. Occam's razor is actively used in disciplines such as biology, physics, and sociology, demonstrating its universality and effectiveness in various fields of knowledge. The need for extraordinary evidence for extraordinary claims is the cornerstone of the scientific method and is discussed in the context of hypotheses about ancient prehistoric civilizations, such as Atlantis or the civilization of ancient astronauts. For instance, if someone claims that in Atlantis they built megaliths comparable to Egyptian pyramids, archaeological findings that confirm this are necessary. For example, if there are suggestions that in prehistoric times, sources of energy similar to those we know today were used, this must be supported by scientific research that can identify the remaining traces of these technologies. Otherwise, such hypotheses remain nothing more than speculations. The scientific community demands clear evidence to accept such claims, and this is justified because without sufficient data, they can easily become myths or conspiracy theories. For example, many of the so-called proofs of the existence of ancient technologies often rely on interpretations that do not withstand criticism. To confirm or refute such hypotheses, long-term research and thorough analysis are required. This not only requires resources, but also time, making such research complex and expensive. Ultimately, to speak of the existence of ancient civilizations, these claims must be presented with the utmost rigor and based on factual data, not on assumptions or emotional arguments. Modern scientific methods offer researchers unique opportunities for finding and analyzing traces of ancient civilizations. These methods enable not only the discovery of artifacts, but also their study in context, allowing us to understand how societies functioned in the past. For instance, comprehensive analyses allow for the construction of more accurate models of human behavior, migrations, and social structures. Additionally, the use of interdisciplinary approaches that combine archaeology, anthropology, and other sciences opens new horizons for understanding the interaction between different civilizations. Thus, scientific methods become a powerful tool for reconstructing historical processes, enabling us to see the past more clearly and in detail. The ability to research modern satellite, for instance, in Central America, these methods helped uncover ancient canals and roads that were virtually invisible from the surface. LiDAR, on the other hand, uses laser beams to scan the landscape, penetrating through foliage and lifting the veil over dense jungles. In 2018, researchers in Guatemala used LiDAR and discovered more than 6,000 previously unknown structures, including pyramids and residential complexes, which attest to the complex structure of the ancient Maya civilization. For example, in Cambodia, scientists used LiDAR scanning to uncover the ancient city of Angkor, which was hidden under a layer of vegetation, changing our understanding of the scale and significance of the Khmer civilization. Such research shows that the application of satellite mapping and LiDAR technologies not only speeds up the search process, but also significantly enhances its effectiveness, allowing archaeologists to focus on more promising areas for excavations. Methods of mass spectrometry and isotopic analysis have become essential tools in the arsenal of modern archaeologists for determining the age and origin of materials. Mass spectrometry allows researchers to study the chemical composition of samples by dividing them into ions and measuring their mass, enabling precise identification of the elements or compounds present in the material. For instance, analysis of carbon isotopes can date organic remains, such as wood or bone, to several thousand years. Moreover, isotopic analysis can reveal unusual isotope ratios that may indicate technological processing of materials. For example, similarly, lead analysis in metals can help determine their source, as different regions have unique isotopic signatures. These studies using mass spectrometry have already shown that some ancient cultures used materials sourced from significant distances from their places of residence, challenging traditional notions of local production. Modern technologies, such as computer modeling and simulations, play a crucial role in the reconstruction of ancient ecosystems and climatic conditions. Scientists use complex algorithms to create virtual models that depict climate changes over thousands of years. For instance, a study conducted by a group of climatologists revealed that around 10,000 years ago, at the end of the last ice age, temperatures in some regions could have been several degrees higher than today, fostering the growth of vegetation and consequently the establishment of the first human settlements. For example, modeling floods in the Tigris Valley showed that such events could have led to periods of economic decline and population migration. This opens new horizons for understanding the dynamics of ancient civilizations and their adaptation to changing environmental conditions. Thus, the application of such technologies allows not only the analysis of historical data, but also the creation of a comprehensive picture of the interaction between humans and nature throughout different epochs. Scientists continue to accumulate data in their models to make even more accurate predictions about how climatic changes could impact the future of humanity. Recent research indicates that such models can be used not only for the analysis of ancient, but also modern ecosystems, revealing patterns that could help solve contemporary environmental problems. The concept of the Anthropocene examines an epoch in which human influence on nature has become so significant that it alters the fundamental processes of the Earth. Unlike this, scientists note that the scale of these changes is comparable to natural catastrophes, such as mass extinctions, but their cause is human activity. Human influence is even felt in the most remote corners of the planet, where traces of human activity can be found in deposits and soil composition. This leads to ecosystems losing their resilience and animal and plant species facing threats. For example, research shows that this phenomenon extends beyond ecology, affecting economics, politics, and even socio-cultural aspects. People are not just consumers of resources, but also active participants in the process of ecosystem change. Research, for instance, some experts propose using principles of sustainable development that balance human needs with the preservation of natural balance. This could lead to new forms of interaction between humans and their environment. Analyzing current changes, specialists also emphasize the need to integrate ecological knowledge into educational programs and policy to prepare future generations for the challenges the Anthropocene will bring. The application of such knowledge could be the key to creating a more harmonious coexistence between humanity and nature. It is important to note that in this context, both scientific and cultural aspects are discussed, as the perception of nature and responsibility for it varies across different societies. For example, in some cultures, humans are seen as part of nature, not its owners, which can influence approaches to environmental protection. Ultimately, the Anthropocene forces us to rethink our views on nature and our place within it. Specialists continue to explore how to use knowledge about complex interactions in ecosystems to create a sustainable future. This opens new horizons for scientific research and practical application of knowledge aimed at improving the state of our planet. Researchers emphasize that it is essential not to underestimate the influence of social and economic factors on ecological processes. The plastic layer in sedimentary deposits will become a unique geological marker of human civilization, preserving itself for millions of years after our disappearance. This layer is formed as a result of the massive consumption of plastic, which began in the mid-20th century. By the year 2225, it is estimated that there will be more than 32 million tons of plastic waste in the oceans. Future geologists discovering this layer will be able to accurately date it and determine that it corresponds to the era of active plastic use. For example, plastic bottles can remain in the environment for up to 90 years, while some types of plastic can last even 1,000 years. This means that future researchers analyzing sedimentary rocks will be able to see a clear boundary indicating human impact on the planet. While other materials, such as wood or paper, decompose much faster, plastic creates what is known as a plastic horizon in geological layers. This marker will indicate not only our consumption, but also the ecological consequences of emissions and pollution. Research shows that this horizon will differ in composition depending on the region, as different countries use various types of plastic materials and have different waste management systems. In some places, this layer will be saturated with microplastics, which are already penetrating ecosystems worldwide. In other regions, whole items such as toys and containers can be found preserved in sediments. Scientists have already begun using this unique marker to study changes in the biosphere and understand how humanity has affected the climate and ecosystems. For example, the analysis of sediment layers in the world ocean shows how the level of plastic pollution has increased with population growth and industrialization. In the future, the plastic layer will not only be a testament to consumer society, but also a warning about the consequences of unrestrained use of synthetic materials. Global samples. For instance, these are specifically the level of carbon dioxide in the atmosphere before the industrial era was around 260 parts per million, whereas in the 20th century, this figure exceeded 400 parts per million. Such an analysis, for example, studies have shown that the level of sulfur in the atmosphere has decreased sharply in the last 100 years, due to the transition to cleaner energy sources and the implementation of environmental regulations. Therefore, in this context, the analysis of ice cores can become one of the key tools for studying the long-term consequences of human activity on the climate and ecological systems of the planet. Massive species extinction, driven by human activity, will become a prominent biological marker in the fossil record, which future researchers will be able to study for millions of years. According to the International Union for Conservation of Nature, we are currently experiencing the sixth mass extinction, which differs from previous ones in its pace and causes. The causes of this process can be divided into several categories: destruction of natural habitats, climate change, environmental pollution, overexploitation of resources, and introduction of invasive species. For example, deforestation for agriculture and urbanization has sharply reduced the populations of many species living in tropical forests, such as the Amazonian monkey and jaguar. Scientists predict that if current trends continue, up to 50% of all species on the planet could disappear in the next century. These events will leave a noticeable mark in the geological record, and future researchers, analyzing layers of sedimentary rocks, will be able to clearly see how human activity has altered the biosphere of Earth. They will find fossils that will testify to how evolution of species was interrupted by unpredictable changes caused by one of the most destructive factors, human intervention. Civilizations, like nature, are subject to cycles, flourishing, decline, and rebirth. The might of ancient empires such as Rome or Babylon seemed unshakable, but their fall was due to numerous factors: economic crises, internal conflicts, and external threats. One era gives way to another, and in place of once magnificent cities, ruins often remain. Many modern societies grapple with problems familiar to their predecessors: economic inequality, political conflicts, and ecological crises. Paradoxically, despite technological advancements, humanity often finds itself repeating old mistakes. Against this backdrop, it is worth considering what lessons we can learn from history and whether we have the ability to change our fate, or if we are merely puppets in the hands of destiny. Many philosophical contemplations on this question continue to stir the minds of scholars and thinkers over the centuries, and the study of historical cycles only underscores the complexity of human nature and the dynamics of societal development. Thus, by studying the past, we can better understand how to avoid repeating mistakes and perhaps find new paths for future civilizations. In this context, it is important to note that each culture leaves behind unique artifacts and evidence that can serve as keys to understanding the causes of their flourishing and decline. For example, archaeologists discover traces of ancient settlements that tell us about how people lived, worked, and interacted with each other, providing valuable clues about what might have led to their disappearance. The concept of the Great Filter from Fermi's theory posits a hypothetical barrier that restricts the development and long-term survival of technological civilizations in the universe. The idea is that at some stage of evolution, civilizations encounter significant obstacles that could lead to their extinction or severe decline. These barriers can be either external or internal. Internal barriers could be related to social, economic, or technological issues, such as resource depletion, ecological degradation, or conflicts arising from inequality. Others suggest that we are still in the early stages and are merely awaiting the serious challenges that lie ahead. Regardless, the existence of the Great Filter explains why we do not observe many highly advanced civilizations, despite the vast number of potentially habitable exoplanets around other stars. For instance, studying the history of past cultures can help us better understand how to avoid repeating their fate. Throughout this raises an intriguing question. If such civilizations, possessing knowledge and technologies, could bring about their own destruction, what are the chances that other, possibly earlier or even more advanced intelligent beings that once existed on Earth would have met a similar fate? Furthermore, technological progress often goes hand in hand with increased resource consumption and environmental degradation. These factors can trigger a chain reaction, leading to the collapse of an entire civilization. For example, it is likely that many civilizations in the past were unable to overcome these barriers, which explains the absence of their traces in the archaeological record. Today, we have only remnants of past epochs, such as mysterious megaliths or undeciphered inscriptions, which hint at the existence of highly advanced cultures. These facts underscore the vulnerability of even the most powerful societies in the face of their own mistakes and external threats. Investigating these issues reveals that self-destruction is not just a theoretical abstraction, but a real threat that any civilization reaching a certain level of development might encounter. In some cases, it may even be the cause of our solitude in the universe. For example, in the search for extraterrestrial intelligence, the SETI programs have not found any signals, which could also indicate that most civilizations do not survive to the stage of interstellar communication. The concept of sustainable development offers an intriguing perspective on the possible path of evolution for intelligent species. It suggests that civilization can reach a level of development where it maintains harmonious relationships with the ecosystem of its planet. This means, for instance, sustainable development also implies social justice and economic stability, which can prevent conflicts and wars over resources. As a result, such civilizations could exist for millions of years without facing catastrophic consequences, as seen in many contemporary societies on the brink of ecological crises. A crucial aspect of this concept is that intelligent species can develop their technologies and culture in harmony with their environment, opening the door to long-term survival. This scientific research shows that a community working together towards sustainable development can create more robust and stable living conditions, as evidenced by examples of tribes and peoples who have successfully lived in harmony with nature for thousands of years. Space archaeology is a relatively new field that combines archaeological research with space technologies. It studies not only terrestrial civilizations, but also traces of human activity on other planets and moons, as well as the impact of the space environment on cultural development. For instance, satellite imagery allows archaeologists to discover hidden structures and artifacts that are invisible from the ground. A significant scientific research conducted with orbital spacecraft and rovers can provide insights into how technologies and cultural practices evolved in various ecosystems. One of the key tasks of this field is understanding potential signs of life on other planets, which could lead to the discovery of new forms of cultural heritage. This approach not only broadens the horizons of archaeological research, but also poses important questions about what it means to be human in the context of the vastness of the cosmos. Research in this area continues to develop, attracting the attention of scientists and enthusiasts worldwide. Searching for artificial structures on the Moon is becoming increasingly relevant, especially when considering the possibility of traces left by ancient civilizations. For instance, if structures similar to the pyramids in Egypt or the megaliths in Britain ever existed on the Moon, they could have remained untouched for millions of years. These findings spark debate among scientists. Some believe they are merely natural formations, while others are convinced they could be the result of intelligent beings' activities. These discoveries have fueled discussions about whether ancient civilizations left their marks on the Moon and what role this could play in understanding not only the Moon's history, but also our place in the cosmos. It is worth noting that with each new launch and research mission, there is an opportunity to learn more about such potential artifacts. Research into Mars in search of signs of life has captivated scientists and researchers since the beginning of the space age. According to recent data, the red planet once had conditions conducive to the development of complex life forms. For instance, scientists believe that these water resources could have created an environment suitable for the emergence of life. Missions like Spirit and Opportunity discovered minerals that form only in the presence of water, such as clay minerals and sulfates, confirming the presence of liquid water in the past. Recently, the Mars rover Perseverance began searching for organic molecules and other possible biomarkers that could indicate the presence of life. The instrument known as MOXIE has already successfully produced oxygen from carbon dioxide, opening up prospects for future colonies. These investigations underscore how close we are to understanding Mars's history and open up new horizons for the search for possible artifacts that could tell us about how life might have evolved on this planet. Furthermore, the Mars 2020 mission continues to collect data on the planet's climate and geology, which may also shed light on Mars' past. One of the most intriguing directions in the search for extraterrestrial life is the study of altered asteroids and other small bodies in the solar system. Scientists believe that some of these objects might harbor traces of activity from technologically advanced civilizations that may have used them as resource sources. Furthermore, there is a hypothesis that ancient civilizations could have used such asteroids for mining metals or other valuable materials, which is supported by the discovery of meteorites with unusual isotopes that may indicate technology for processing materials. Scientists also study small bodies like comets, which may contain organic molecules, suggesting that life on Earth could have originated from materials delivered by other celestial bodies. Observing the movement and composition of these objects opens new horizons for understanding not only the history of the solar system, but also the possibilities of life beyond Earth. As a result of such research, scientists hope to find evidence that will confirm or refute the existence of highly advanced civilizations in our galaxy. In this context, the asteroid Itokawa, which contains heavy metals such as nickel and cobalt, is of interest, as their presence may indicate that asteroids were used in technological processes. This idea encompasses various approaches, from altering climate to transforming planetary surfaces to make them more Earth-like. For instance, scientists are exploring the possibility of terraforming, where a planet's atmosphere, temperature, and even geology can be altered to create favorable conditions for life. This could involve creating artificial oceans or modifying the atmosphere to increase oxygen content. Since the focus on such issues highlights not only scientific interest, but also practical applications that could have significant consequences for future colonies on other planets. However, these questions require serious discussion and analysis before such projects can be practically implemented. Nevertheless, planetary engineering opens doors to new possibilities that once seemed like science fiction. This approach involves large-scale manipulations of the atmosphere, hydrosphere, and biosphere to adapt the planet for human habitation. For instance, on Mars, a planet with a thin atmosphere and low temperatures, terraforming could involve creating a greenhouse effect by releasing greenhouse gases such as carbon dioxide to raise the temperature and increase atmospheric pressure. In addition, for example, if plants were planted on Mars, they could change the composition of the soil and atmosphere, creating new layers of minerals and organic materials that would eventually fossilize. These changes could be recorded in the planet's geological history, making terraforming not only a tool for improving living conditions, but also a potential factor influencing the planet's future geology. For instance, human activity on Earth has already led to significant changes, such as deforestation and agriculture, which leave traces in the form of altered topography and new types of soil. Traces of a highly advanced civilization can be found not only in the form of altered landscapes, but also in the megastructures it created, which could outlast the civilization itself. For example, more ambitious projects, such as orbital rings consisting of massive structures that could encircle a planet, would leave enormous traces in space. These rings could be used for transporting resources or even for creating living conditions in space. Space elevators that could connect the Earth's surface to orbit also represent an interesting example of megastructures. They could be built from ultra-strong materials like graphene or carbon nanotubes, and their remains could be found on Earth as debris or foundations if the civilization that created them vanished. Scientific research shows that such structures are theoretically possible, but their realization requires technologies that are currently beyond our capabilities. Nevertheless, if such a civilization did exist, its megastructures could become important objects for future archaeological studies, helping us understand the level of technological development and societal organization. Fractal architecture is based on repeating geometric forms that can be observed in nature, such as leaves of trees, snowflakes, and bone structures. This concept implies that buildings and other structures can be designed not only to harmonize with the surrounding environment, but also to have characteristics similar to natural forms. For example, architects and engineers take as a basis mechanisms that nature has already perfected to create sustainable and efficient buildings that can regulate temperature, collect rainwater, or even purify air. In some cases, such buildings may appear as if they grew out of the earth rather than being built by humans, thanks to the use of organic forms and eco-friendly materials. These approaches to design not only improve human interaction with nature, but also help create sustainable ecosystems in cities. For example, in the future, such constructions may become the standard in architecture, as they offer not only aesthetic appeal, but also functionality, promoting human integration into natural processes. Projects utilizing fractal and biomimetic concepts already demonstrate how it is possible to create spaces that are not only beautiful, but also naturally integrated into their surroundings. In such conditions, there arises a need to rethink design standards that have so far been based on traditional linear forms often ignoring natural characteristics. Culture, it manifests in the disregard of unique characteristics and traditions that shape the identity of various groups. This phenomenon arises from several factors, including stereotyping, where certain traits are associated with one culture while all other aspects are ignored. Cultural blindness can also result from a lack of education or experience interacting with other cultures, leading to a superficial understanding of the world. It is, furthermore, cultural blindness can be exacerbated by mass media, which frequently presents simplified and stereotypical images that do not accurately reflect the complexity of cultural practices. Consequently, this approach creates a distorted view of the world where diversity and multiplicity remain unnoticed. It is important to acknowledge that each nation has its own unique traditions, customs, and values that need to be taken into account to avoid cultural blindness. Cognitive biases play a significant role in how scientists perceive and interpret data, especially when it comes to unusual hypotheses, such as the existence of prehistoric technological civilizations. First, there is confirmation bias. Researchers tend to seek and interpret information in a way that confirms existing theories, while ignoring data that contradicts their beliefs. This can lead to even compelling evidence of the existence of highly advanced civilizations in prehistoric times being met with skepticism and not being taken into account. Furthermore, group effects come into play. Scientists working within homogeneous communities may feel pressure to adhere to accepted opinions, further complicating the acceptance of unusual ideas. In this context, it is worth recalling various examples where discoveries, such as those in Tibet or mysterious artifacts in South America, sparked heated debates and controversies, but ultimately remained on the margins of scientific discourse due to the fear. Therefore, despite the existence of facts indicating the presence of technologies in prehistoric times, many researchers continue to ignore these data due to the aforementioned biases and prejudices. Scientific research often overlooks the fact that intelligence can take various forms, and technological development does not necessarily have to follow the same path as that of humans. For instance, certain biological species, such as dolphins or crows, exhibit high levels of intelligence, but their evolution has not led to the creation of technologies similar to human ones. This challenges our conventional model, where humans are seen as the pinnacle of evolutionary progress. Moreover, anthropocentrism limits our understanding of how other civilizations might have developed. Research unconstrained by anthropocentric views opens up new horizons for understanding. For example, in archaeology, traces of technologies are found that seem unlikely to have been created by humans, such as the use of complex tools by some animals or the possibility of civilizations with unique forms of consciousness. These discoveries raise questions about how we define intelligence and technology. Scientific paradigms are often too narrow, preventing us from seeing a broader context of the development of reason and technology in nature. It is important to understand that evolution does not necessarily follow a linear trajectory, and the diversity of life forms can lead to entirely different outcomes. Research shows that in the past, there existed other forms of intelligence that do not fit into our usual models, as evidenced by findings such as tools found in layers dating back tens of thousands of years, which could have belonged to beings other than humans. The problem of recognizing technologies that are radically different from our own is a pressing issue for many archaeologists and historians. For instance, if an ancient people used processed plant fibers or organic compounds for construction instead of stone or wood, such structures could be easily destroyed by time and leave no discernible traces. Moreover, research indicates that many technologies could have been based on principles that now seem fantastic or even impossible. For example, there are theories that some ancient societies used sound vibrations to process materials, which have not yet been adequately confirmed by archaeology. As a result, every discovery requires careful analysis to avoid missing something that could fundamentally alter our understanding of history. For example, some tools from the Copper Age could have been made using methods that we do not know, which calls into question the effectiveness of our dating and analysis methods. Parallel technological paths refer to the concept that different civilizations could develop their technologies independently of one another, creating unique solutions to similar problems. This implies that some societies could reach similar achievements without direct contacts or influences from each other. For instance, this also raises questions about how we understand the evolution of technologies and historical connections between cultures. Many researchers suggest that the lack of written evidence does not always mean the absence of contacts between civilizations, as knowledge exchange could have occurred orally or through human migration. Therefore, for example, thus the same solutions could be used in different places with completely different purposes and meanings, adding depth to our understanding of historical processes. Just as different peoples independently invented the wheel, they could also have created other technologies that then became the foundation for further civilizational achievements. In this context, the concept of parallel technological paths becomes a key concept for studying not only the history of technologies, but also the very nature of human development. Humanity did not simply copy from each other, but developed independently based on its unique circumstances and needs. For instance, let's consider how this could look. In such a world, animals capable of performing specific tasks, such as transporting goods or assisting in agriculture, might be bred without the need for complex mechanical systems. These organisms would possess unique characteristics, enabling them to function in specific conditions, eliminating the need for traditional archaeological artifacts like tools or construction materials. Instead of factories and plants producing goods, biofactories might emerge, where living organisms would be used to obtain necessary resources. One of the most captivating theories regarding the potential development of ancient civilizations is the idea of quantum technologies that could manipulate fundamental forces of nature. Imagine a civilization capable of using quantum effects to control matter and energy at the microscopic level. Such technologies might include the creation and destruction of material objects, the manipulation of gravity, or even the control of time without leaving behind familiar artifacts. This civilization could, for instance, create devices that utilized phenomena such as quantum entanglement or tunneling, allowing them to interact with the surrounding world at a level currently beyond our reach. This could explain why archaeologists find no traces of such highly advanced technologies. They simply did not leave behind physical objects for us to study. Moreover, some researchers even suggest that ancient texts and myths may contain hints of such technologies, describing events that appear to involve the manipulation of physical laws. For instance, legends of flying objects or the disappearance of people could be metaphors for the use of technologies that we cannot comprehend within the framework of our current science. Such contemplations open new horizons for research, allowing us to view history from a completely new perspective. In this light, it is also important to note that such theories require a deeper study and possibly even new approaches to archaeology and history to shed light on what we cannot yet see, based solely on traditional methods of research. These technologies can encompass systems for transmitting knowledge and culture through oral traditions, myths, and legends that are preserved in the collective memory of generations. For instance, the languages spoken by various peoples can be seen as sophisticated systems for encoding and decoding information, conveying not only facts, but also emotional and cultural aspects of life. Contemporary research indicates that such technologies can include symbolism and rituals that help shape collective consciousness and community identity. They could have thrived in societies where writing was not necessary or did not exist, but where the importance of transmitting knowledge through oral practices was critically important for survival. Additionally, it is worth noting that such immaterial technologies can include mathematics, music, and other forms of art that serve as means of communication and information transfer, creating bonds between people. For example, some indigenous peoples of Australia have complex musical systems that convey information about the location of resources and cultural values. These practices allow us to see how intelligent beings could develop methods of connection and interaction without the need for physical infrastructure. In such societies, technologies could exist as concepts and ideas that are transmitted and transformed over time, adapting to changing conditions and needs. Based on generations, such reflections open up new horizons for understanding history and the evolution of human consciousness. The study of aspects such as collective memory and cultural narratives can provide us with a deeper understanding of how various societies interacted with each other and adapted to their environment. It is important to note that in the absence of material artifacts, such as written documents or buildings, the search for traces of these immaterial technologies requires researchers to employ new approaches and analytical tools. The concept of planetary consciousness encompasses the idea that humanity, as a whole, is capable of a deeper understanding of its place in the world and its interconnection with the surrounding environment. In this context, it is important to note that planetary consciousness implies awareness of global issues such as climate change, loss of biodiversity, and social inequalities. For example, research shows that transitioning to sustainable energy sources can significantly reduce the carbon footprint, thereby influencing the planet's climate conditions. Cultural aspects also play a crucial role here. How different communities perceive their connection to nature and which traditions and practices they use to preserve ecosystems. For instance, such approaches can serve as a model for many modern societies striving for a more harmonious coexistence with nature. Furthermore, planetary consciousness can be linked to the development of technologies that facilitate the exchange of knowledge and experience between different cultures, thereby strengthening collective understanding of global challenges. Technologies such as the Internet allow people from different parts of the world to interact and share ideas, creating a new platform for cooperation. For example, various environmental initiatives based on the Internet enable people to unite to protect the environment and share successful practices. A key aspect here is that planetary consciousness is not static. It evolves and changes in response to new challenges and opportunities presented by the modern world. This process requires active participation from each individual, which in turn underscores the importance of personal responsibility in the context of global issues. Thus, attention to planetary consciousness can lead to the formation of new social norms and values oriented towards sustainable development and harmonious coexistence. In this context, it is worth mentioning that the awareness of the interconnectedness of all living beings and ecosystems can serve as a foundation for creating a more just and sustainable society. Humanity is at a crossroads where it is necessary to make decisions about how to move forward to ensure the well-being of future generations. In this sense, planetary consciousness is not just an idea, but a necessary step for the survival and prosperity of our planet. Lovelock, for example, plants produce oxygen, while microbes decompose organic matter, returning nutrients to the soil, creating a closed cycle. In this context, the question arises, how does our behavior and decisions affect this planetary self-regulation? Lovelock asserts that understanding Earth as a living organism will help us better understand the consequences of our actions and the need for sustainable development. In this context, it is also important to consider how other cultures and philosophies perceive Earth and nature, which could enrich our understanding of planetary intelligence. Imagine each of these microorganisms not just as a single cell, but as part of a complex global neural network where continuous information exchange occurs. For instance, microbes in soil can exchange substances that help them adapt to climate changes or the presence of toxic substances. This system of interactions can be seen as a kind of brain of the planet, responsible for maintaining the viability of ecosystems. It is important to note that this form of consciousness is not individual, but a synergistic effect arising from the interaction of many microorganisms, which collectively can make decisions affecting their habitat. In fact, their actions can be directed towards both survival and the optimization of conditions for other organisms, creating complex interconnections within the ecosystem. The study of this collective consciousness opens new horizons for understanding biodiversity and sustainable development, highlighting the importance of the microbiological community in maintaining balance on the planet. For example, research shows that changes in the composition of the microbiome can lead to significant ecological consequences, including climate change and loss of biodiversity. Fungal mycelial networks represent a remarkable and complex mechanism that could serve as the foundation for a planetary communication system. These mycelium actively interacts with plant roots, forming symbiotic relationships known as mycorrhiza. In these relationships, trees can exchange nutrients and even stress signals, such as warnings of insect attacks. Research indicates that mycelial networks have been functioning for hundreds of millions of years, making them one of the oldest and most resilient biological mechanisms on the planet. These networks not only ensure ecosystem stability, but also support complex communication processes that can impact the health of the entire forest ecosystem. Within this interaction, fungi can also decompose organic matter and contribute to the cycling of nutrients, making them an integral part of the ecosystem. For instance, some scientists even suggest that such networks could be used for interspecies information exchange, opening new horizons for understanding natural interactions. There is evidence that mycelium can detect and report the presence of pathogens, warning other plants of danger. Therefore, mycelial networks of fungi not only support life in ecosystems, but also represent a unique example of a natural communication system that has been helping ecosystems adapt and survive for millions of years. Extensive research shows that this form of communication may be more complex than we previously thought. Temporal chauvinism is a concept that implies the superiority of a particular epoch or historical period over others. This phenomenon manifests in how people assess the achievements and culture of preceding generations, often disregarding their significance. For instance, many believe that contemporary science and technology are the sole expressions of progress, while the achievements of ancient civilizations such as Mesopotamia or ancient Egypt often remain in the shadows. Temporal chauvinism can also be reflected in educational systems, where emphasis is placed on contemporary events, while important historical lessons and achievements of previous epochs may be undervalued or omitted from curricula altogether. This creates a distorted perception of history, where new ideas and achievements are seen as the only possible ones, thereby hindering the understanding of how the past influences our present. Respect for the achievements of different epochs can enrich our understanding of cultural heritage and help us see how various ideas and concepts have evolved over time. It is important to remember that many contemporary achievements are based on knowledge and discoveries made in the past, and ignoring this fact can lead to the loss of valuable historical perspective. Modern people often tend to perceive past eras as less developed and primitive compared to our time. This widespread opinion is shaped by the influence of modern technologies and scientific achievements, which seem to us as the pinnacle of progress. However, such a perception overlooks the possibility of the existence of highly developed civilizations in ancient times. For instance, in Mesopotamia, in the 7th millennium BC, the Sumerians created one of the earliest known writing systems and began to keep records and develop mathematics. In India, many people find it hard to imagine that ancient peoples could possess knowledge and technologies that evolved over centuries and could have influenced our current understanding of the world. This bias often leads to the neglect of archaeological findings that challenge traditional notions of the primitivity of ancient societies. For example, in the 21st century, artifacts were discovered indicating the presence of complex social structures and economic systems in ancient civilizations. It is important to note that many of these cultures flourished long before our time, and their achievements in science, art, and architecture can challenge our understanding of the linear evolution of human civilization. People who believe that science and technology are exclusively a product of modernity often fail to consider that many of their foundations were laid precisely in those ancient times. The cyclical nature of history is not just a theoretical concept, but a real process that can be observed over many millennia. For instance, in Mesopotamia, there have been 3 major periods of civilization's rise and fall, from the Sumerians to Babylon. Similar processes can be traced in other parts of the world. Ancient Egypt experienced periods of prosperity, followed by dynastic crises and foreign invasions. In India, powerful empires, such as the Mauryan Empire, reached their peak and then declined. Throughout Earth's geological history, numerous examples can be found where one civilization left behind a legacy that became the foundation for new ones, while others vanished due to natural factors or internal conflicts. These cycles influence social, economic, and ecological aspects. For example, changes in climate during certain epochs could have been the catalyst for the demise of entire civilizations, as was the case with the Maya. Scientific research shows that nature abhors a vacuum. New societies often emerge on the ruins of fallen ones, potentially repeating the mistakes of their predecessors. Consequently, history is not a linear sequence of events, but a complex pattern where each thread intersects with others. creating the diversity of human experience. Current have been discovered, leaving behind many unanswered questions. For instance, many ancient peoples, such as the Minoans, disappeared after powerful natural disasters, including volcanic eruptions and earthquakes, which destroyed their centers and wiped out entire cities. This not when people, for example, cultural collapses, such as the fall of the Roman Empire, also contributed to the loss of knowledge. In such times, when civilizations faced crises, knowledge about technologies, medicine, and art could be lost forever, leaving behind only scattered artifacts. For example, this state allows one to see oneself as part of something greater than just everyday life, and to recognize one's role in the complex web of existence. Those who reach this level of consciousness can feel a deep unity with nature, other people, and even cosmic phenomena. They begin to perceive their actions as reflections of broader cosmic processes, which can lead to changes in their behavior and worldview. For instance, such individuals may consciously address environmental issues, understanding that their actions affect the planet. This state can evoke strong emotions such as inspiration and awe when contemplating the starry sky or the grandeur of nature. Furthermore, cosmic consciousness is often linked to an inner drive towards harmony, which can manifest in creativity or spiritual pursuits. These experiences often lead to changes in life as people begin to seek deeper meanings and values. In this this opens up interesting possibilities for discussing ancient intelligent beings. If life indeed came from outside, the question arises, could these extraterrestrial forms of life have been more advanced and perhaps even possessed intelligence? In some ancient cultures, one can find references to gods who descended from the heavens and taught humans various skills. For example, these stories can be interpreted as consequences of contacts with highly developed civilizations. Additionally, research on meteorites, such as the Allen Hills meteorite, in which organic molecules were found, further fuels interest in this hypothesis. Such discoveries raise questions about how diverse life in the universe might be and how it could have interacted with our planet. Scientific experiments, such as studying microbes in space conditions, show that some organisms can survive in a vacuum and at high levels of radiation, which further supports the panspermia hypothesis. This idea is based on the assumption that intelligence is not a unique property of Earth, but may be present everywhere, including in the most unexpected places. For instance, some researchers believe that intelligence can exist as a collective intelligence that connects living organisms on planets, creating a unified consciousness capable of perceiving the surrounding world and adapting to it. In this context, intelligence can manifest not only in technology or biological forms, but also in conditions that we cannot yet imagine. This could be something like energies that inhabit cosmic space and can interact with material forms of life. Theories about cosmic intelligence also encompass concepts that suggest consciousness can be transmitted through stars or even exist in symbiosis with physical objects such as planets or stars. A notable example is Stanisław Lem's novel Solaris, where the ocean on the planet Solaris exhibits consciousness, interacting with researchers, creating their memories and dreams. This concept raises numerous questions about the nature of consciousness, its possible existence outside biological forms, and how we might interact with such forms of intelligence. Research in the fields of neuroscience and quantum physics also raises questions about where individual consciousness ends and something more expansive begins, which could be inherent to the entire universe. Quantum entanglement is one of the most intriguing and mysterious concepts in quantum mechanics, which could serve as a theoretical foundation for information transmission between intelligent beings over vast distances. This phenomenon involves two particles becoming interconnected in such a way that a change in the state of one particle instantaneously affects the state of the other, regardless of the distance between them. For instance, if one particle is measured and its state changes, the other particle, even if it is at the other end of the universe, will immediately adopt the corresponding state. This raises questions about how such technologies could transform our understanding of communication in space, creating potential for instant information exchange between distant civilizations. However, it is important to note that realizing such communications would involve overcoming numerous technical and theoretical challenges, including the stability of entangled states and their control over long distances. Nevertheless, quantum entanglement continues to captivate the minds of scientists and draw attention to innovative approaches in the field of communication, opening new horizons for the study and understanding not only of our universe, but also of the possible forms of life that may exist within it. The question of ancient civilizations evokes many reflections on how people perceived the world around them and how these perceptions shaped their lives. For instance, many civilizations associated their deities with natural phenomena such as rain or the sun, highlighting the deep connection between humans and the world around them. However, such worldviews often led to conflicts when one society competed with another, based on differing interpretations of the divine and the human. It is worth noting that despite cultural and religious differences, all ancient civilizations shared a common goal: seeking the meaning of their existence and understanding humanity's place in the vast expanse of the universe. This pursuit of knowledge and understanding, in turn, contributed to the development of the earliest forms of science and philosophy, which, although rooted in different traditions, ultimately led to what we now call civilization. In the year 681 BC, in Mesopotamia, residents began to use solar and lunar calendars, marking an important step in the development of agriculture and the organization of social life. Consider, for instance, did they have their own philosophical schools of thought and understanding of the universe? What were their achievements in science, art, and culture? This question sparks interest in how various environmental conditions, such as climate change or geological catastrophes, could have influenced the development of intelligent life. Additionally, can we consider that each new wave of intelligence carries the experience of previous civilizations? Or do they start with a clean slate? Are there any traces that could indicate previous civilizations, such as artifacts or architectural structures that remain unrecognized? No less important is the question of whether these civilizations were aware of their own transience and how this influenced their worldview. Can we learn from their mistakes if they existed? These contemplations raise even more complex questions about our place in the evolutionary chain and how we can make use of our time on this planet. Scientific research in the fields of archaeology and paleontology continues to uncover facts that shed light on these questions. For example, in the 20th century, archaeologists discovered traces of an ancient civilization in the modern-day region of Iraq, which existed more than 6,000 years ago and left behind complex irrigation systems and writing. The concept of cosmic loneliness of humanity suggests that we are alone in the universe, which raises many questions about our significance and place in the cosmos. If archaeologists were to discover traces of ancient non-human civilizations, this could fundamentally change our understanding of ourselves. We are accustomed to believing that intelligent life exists only on Earth, but the discovery of such civilizations would give us the opportunity to re-evaluate our uniqueness. For instance, if artifacts were found that indicate the existence of highly advanced technologies or cultures, this could mean that humanity is not the sole bearer of intelligence. Hypothetically, such civilizations could have existed millions of years ago and left behind not only material evidence, but also cultural heritage that we could study. Such a discovery would spark a storm of emotions and intellectual debates, forcing us to consider how we relate to other forms of life and how they might have influenced our own path of development. Understanding that we are not the only ones to have ever reached a level of intelligence could change our approach to questions related to life on other planets, and even influence the humanistic concepts we adhere to. Research in the fields of astronomy and astrophysics already indicates that there may be numerous exoplanets in our galaxy where conditions could be suitable for life. In the presence of such findings, the notion of human loneliness in the cosmos could be shattered. We could begin to see ourselves as part of a broader community of intelligent beings, which in turn would raise new questions about our responsibility towards other forms of life. Astronomers have discovered more than 4,000 exoplanets, and among them, there are likely to be some that can support life as we know it. The cosmic heritage we have inherited from previous civilizations on Earth poses complex philosophical questions for contemporary humanity. As potential continuators of intelligent life, we bear the responsibility not only for preserving our own culture, but also for studying and understanding the forms of life that existed before us. Each civilization, from the Sumerians who created the first writing system around 3,000 years before our era, to the magnificent Aztecs, has left its mark on history, shaping our understanding of the world. The question is whether, with such a heritage, we can correctly assess our role in the cosmic context. Many philosophers assert that we are obliged to protect and promote intelligent life to avoid repeating the mistakes of our predecessors, such as wars, destruction of ecosystems, and social inequality. We must learn from their examples. For instance, the fall of the Roman Empire, caused by internal political instability and economic problems, serves as a reminder of how prosperity can quickly turn into catastrophe. Therefore, when contemplating our place in the universe, we must recognize that we are not only heirs, but also custodians of knowledge about previous civilizations. This implies the necessity of active participation in ecological and sustainable development issues to ensure a future for subsequent generations. Some scientists even suggest that we might be part of a broader galactic history where intelligent species play a key role. For example, if we could establish contact with extraterrestrial civilizations, it could lead to an exchange of knowledge and technologies, which in turn could change our understanding of life and responsibility. This idea underscores that our heritage does not end with Earth, but has the potential for further development on a cosmic scale. We can be not just spectators, but active participants in this grand cosmic ballet, where every step matters. It is important to remember that each of our actions aimed at supporting life on Earth reflects our responsibility to future generations and to the forms of life that may exist on exoplanets. In this context, it is worth recalling that the concept of cosmic heritage encompasses not only knowledge of the past, but also the desire to create a more harmonious future for all of humanity, capable of understanding and appreciating its place in the universe. In this context, each new discovery or research can add new dimensions to our understanding. For example, the discovery of traces of ancient civilizations on Mars, if confirmed, could fundamentally change our view of life in the universe. For instance, if there were ever intelligent beings on our planet other than humans, the question arises, what is consciousness? Are there different levels or forms of consciousness that we cannot even imagine? In the philosophy of mind, concepts such as panpsychism are discussed, which asserts that consciousness can be inherent in all objects, not just living beings. This raises the question of whether ancient forms of life, such as dinosaurs or even simple organisms, could have possessed intelligence that we do not recognize in our familiar understanding. Additionally, considering that many cultures, including the Sumerians and the Maya, left behind enigmatic artifacts that may indicate the presence of complex thinking, a new paradigm emerges. What if these civilizations were not the only ones to achieve significant levels of intellectual development? Given that some research suggests the possibility of highly advanced civilizations on Earth, such as the Atlanteans, we may ask how they perceived the world and how their rational existence could have influenced the planet's ecosystem. It is also important to note that if we consider intelligence as something more universal than just human experience, we can open new horizons for the study not only of our history, but also of the nature of being itself. Scientists continue to explore various models of the mind, and each of these models reveals new aspects that can explain how and why life on Earth developed as it did. For example, research in the field of neurobiology shows that many animals, such as dolphins and sparrows, exhibit complex forms of communication and social behavior, which may indicate the presence of intelligence in various forms. In this context, it is crucial to consider that we may not understand at all what it is like to be an entity with a different form of intelligence, and what mysteries may lie hidden in our past. The ethical aspects of searching for and studying the traces of ancient civilizations are becoming increasingly relevant in the light of modern scientific research. It is essential to recognize that each artifact discovered during excavations represents not only historical value, but also cultural heritage that may have belonged to extinct intelligent species. Respect for this heritage implies that scientists should approach its study with caution and attention, understanding that every intervention in the Earth can destroy unique evidence of their existence. For instance, many archaeologists now adhere to principles that exclude commercial use of finds, aiming to preserve them for future generations. It is also important to remember that many ancient cultures had their own beliefs about the sacredness of the land and objects they left behind. This raises questions. How can we respect these beliefs if they differ significantly from our own? In some cases, such as the study of Native American mounds in North America, active cooperation with the descendants of these peoples is practiced, which helps to preserve cultural identity and respect their traditions. Other research, such as excavations in Egypt, faces criticism for possible disrespect towards the dead and their culture. Scientists are not only obliged to extract information from the found artifacts, but also to consider them in the context that respects the culture to which they once belonged. In this sense, archaeologists become not only researchers, but also guardians of extinct civilizations, which imposes additional responsibility on them. The complexity of ethical questions increases when it comes to possible technologies and knowledge that could have existed in these extinct societies. How can we account for their achievements and ideas if we cannot fully understand their context? For example, the Maya culture created complex astronomical calendars and architectural monuments. But how is their heritage perceived in the modern world? All these questions require deep reflection and discussion, making ethics in archaeology one of the most important topics in scientific circles. Research projects that ignore these aspects risk not only losing valuable historical data, but also provoking a negative reaction from contemporary society, which may lead to restrictions on further research. It is important that each project be based on respect for the past and the desire to understand, rather than simply to exploit its materials. The modern approach to archaeology requires scientists not only to have knowledge, but also to demonstrate a high degree of social responsibility. Successful study of ancient civilizations is possible only if all these aspects are taken into account, which underscores the importance of an interdisciplinary approach in this field. As a result, ethical norms become an integral part of all research activities, allowing us to better understand and appreciate what we can learn about our past while also respecting those who lived before us. In recent years, debates have intensified about how to preserve the cultural heritage we find and how to best present it to society. The concept of cosmic ethics encompasses ideas about moral obligations that may exist between intelligent beings separated by vast distances in time and space. For instance, if one civilization were to develop technologies for interstellar communication, it would need to consider not only the ethical norms of its time, but also the potential consequences of interaction with other, potentially older or less, advanced civilizations. Debates arise regarding how we should act if we encounter other intelligent life forms. Should we protect them from themselves or allow them to develop independently as our ancestors did? The problem becomes even more complex when considering how to transmit moral norms that may be incomprehensible to other species with entirely different cultural and historical backgrounds. Various theories offer different approaches. Some argue that intelligent beings, regardless of their origin, should adhere to universal moral principles such as respect for life and the pursuit of knowledge, while others maintain that such universal norms may not exist, and each species should make decisions based on its unique circumstances and traditions. For example, if humanity discovered traces of an ancient civilization on another planet, what moral obligations would we have towards its legacy? It is crucial to consider that in such a situation, our interpretation of their culture might be skewed. These questions prompt important reflections on how we perceive not only our past, but also our potential future, where there may be numerous intelligent life forms. Cosmic ethics, therefore, presents not only a philosophical challenge, but also a practical one, requiring us to engage in deep analysis and caution when interacting with entities we cannot fully comprehend. It is essential to remember that in this context, our perception and the potential consequences of our actions on a scale we can barely imagine play a decisive role. Indeed, many scientists raise alarming questions about how we might influence the development of other civilizations if we ever establish contact with them. Heritage for the future is a concept that encompasses not only tangible objects such as buildings and artifacts, but also intangible aspects, including ideas, cultures, and values. We leave, for instance, philosophical teachings, scientific discoveries, or literary works can have a profound impact on people's thinking and behavior in the future. It is important to note that heritage is not always static. It is subject to interpretation and reinterpretation, allowing it to remain relevant in a changing world. People, as they create their societies, will use this heritage as a foundation for new ideas and technologies, as well as for forming cultural identity. The results achieved in the fields of art, science, and technology become part of this heritage, influencing social norms and values. In this context, one can recall how great discoveries, such as electricity or the internet, have transformed everyday life and human interaction. Each new generation interprets the preceding heritage in its own way, which can both enrich and limit their possibilities. A crucial aspect is that we, as a society, must be aware of what we are leaving behind. The legacy we leave behind in history depends on our relationship with our environment and the people who will live after us. In this context, it is worth considering what values we want to pass on and how they will be perceived in the future. Heritage is formed not only by great achievements, but also by everyday actions, making it an essential element of our existence. Ultimately, it is this heritage that will serve as the foundation for future civilizations, which may be even more complex and diverse than we can imagine. It is important to remember that we are already laying the groundwork for future cultures and communities, even if we are not aware of it. Creating long-term messages for future civilizations that may arise on Earth after the disappearance of humanity would be a significant task for any intelligent species. Such messages could include information about our culture, science, technologies, and even how to avoid the mistakes that led to our extinction. For example, ancient Egypt left us with hieroglyphs on the walls of tombs and temples that describe the lives of pharaohs and their achievements. These messages were intended to be read by descendants, but not all of them have reached us in their entirety. Modern researchers can only speculate about what messages from Neanderthals or other preceding intelligent species might have looked like if they had left written records. For instance, we can imagine that future civilizations might find such messages, for example, written on special materials resistant to destruction, or in the form of stone tablets, as in Mesopotamia. Durable messages could contain not only information about our achievements, but also warnings about what might happen if ecological problems or social inequality are ignored. For example, in Scandinavia, Vikings left stone inscriptions that reflected their worldview and beliefs about life after death. Such artifacts show that the desire to leave a mark on history has been a part of human nature for millennia. Research indicates that even if our civilizations disappear, messages can remain in a form that will be understandable to future beings. In this context, one can mention projects like the Golden Record, sent into space on the Voyager spacecraft, which contains information about Earth and its inhabitants for potential extraterrestrial civilizations. This record was designed as a message that should outlast millions of years and reach other worlds. Such examples clearly demonstrate the importance of preserving information for posterity, even if they will be completely different beings than us. Perhaps in the future, someone will find such messages and understand that we were not only beings who built, but also creators of knowledge that we hope will help them avoid our mistakes. Deep-time information repositories represent a concept that piques the interest of scientists and researchers aiming to preserve knowledge over millions of years. One example of such repositories could be specialized underground complexes designed to withstand geological changes and potential catastrophes. These systems can utilize natural materials like clay or salt, which possess high resistance to external influences. For instance, the Seed Vault project in Norway, opened in 2018, stores seeds capable of restoring ecosystems in the event of global catastrophes. However, what can serve as an analog for preserving human knowledge and culture? One idea is the creation of an archive system that stores not only textual documents, but also audio and video recordings, adapted to various storage conditions. In this context, one can envision time capsules that are activated after millions of years, transmitting information about the civilization that created them. Such capsules could contain not only data on scientific discoveries, but also cultural artifacts, algorithms, and language codes. Scientists hypothesize that the use of time-resistant carriers, such as glass or metal plates with engravings, can preserve information in its original form. For example, in the year 2000, a group of researchers discovered records on glass plates created more than 100,000 years ago. These records could shed light on the lifestyle and thought processes of people from that era. Thus, the concept of deep time information repositories opens new horizons for inter-civilizational communication, enabling future generations to connect with the experiences of their predecessors, even if they are separated by geological epochs. In such conditions, information can serve as a link between different civilizations, which is particularly relevant in the context of studying potential colonies on other planets, where preserving knowledge about Earth will become critically important. Scientists have already begun developing technologies to adapt such repositories to the conditions of other planets, utilizing resources available on-site. The concept of cosmic altruism emerges from the assumption that highly advanced civilizations may deliberately leave knowledge and technologies for future intelligent species, even if they never meet them. For instance, if we consider the perspective that such civilizations might observe the development of less advanced but potentially intelligent species, the question arises, do they have a moral obligation to share their achievements? In some scientific circles, this concept is also discussed in the context of the search for extraterrestrial intelligence, where scientists believe that if we ever discover traces of another civilization, it might be a result of their conscious effort to leave a trace. Examples of this can be seen in ancient texts and myths, where gods or wise men impart knowledge to humanity, reflecting our hopes that life can be not only self-centered, but also altruistic. In the cosmos, this can manifest through cosmic messages, or messages that highly advanced civilizations might leave on planets or asteroids, assuming that someone might find them someday. Such messages could contain not only scientific knowledge, but also philosophical ideas that, in their view, could help new species avoid catastrophes or destructive conflicts. In this context, one can recall projects like Voyager, which sent golden discs with information about Earth into deep space as a symbol of hope that someone might find them. The idea of cosmic altruism, therefore, is not just a utopian dream, but a serious concept that could change our understanding of humanity's place in the vast expanse of the universe. Scientific research and discussions in this area continue, fueling interest in how we perceive our future and our connection with potential descendants on other planets. The question of the existence of ancient prehistoric civilizations remains open and is a subject of debate among scientists and researchers. Some believe that highly developed societies may have existed on Earth long before the known civilizations such as Sumer or ancient Egypt. For instance, in India, archaeologists have discovered the ruins of the Harappa civilization, which flourished around 4,000 years before our era and possessed a system of urban planning and drainage systems, challenging the notion that such achievements were only characteristic of later times. If we consider this from another perspective, we might ask, were we the first technological civilization on Earth, or just one of many that for some reason have faded from historical memory? This question prompts us to re-evaluate the history of our planet and our place in it. Our responsibility for preserving life and reason on Earth becomes particularly acute in light of potential threats such as climate change and ecosystem catastrophes. All this encourages us to reflect on how we can use knowledge of the past to avoid repeating mistakes and build a sustainable future. As you prepare to sleep, consider the endless possibilities that lie within the depths of time and space, and the traces we will leave for future generations. After all, each new day is a new page in the history of humanity, which we write with our actions and decisions. In every day, there are not only challenges, but also opportunities for change that can shape the destinies of millions.